Oh, okay, okay. Fine. So, dear Yuval and dear ex-colleagues, present colleagues, dear friends, it's a great honor and a great pleasure for me to be here today to attend this meeting and to give a small contribution to the celebration of your 80th birthday. Indeed, I still remember the days that Shimon was talking about. I mean, the time I was a PhD student here, 66, 68, with some nostalgia. And indeed, the fact that we were periodically coming to Tel Aviv from Rehovot, especially when Yuval would have been coming back from a trip to the US, and would tell us about the latest news across the Atlantic, what was going on, what were the opinions there, what were the trends. Now, almost 40 years later, Yuval in February sent me a fax from Brussels 2 days before I gave this inauguration lecture for my Collège de France chair, in perfect French. Yesterday I understood that you studied also in France for some time. There was just one thing which shocked me a little bit. In all the letter, he was giving me vous. You were putting vous instead of tu, which I found a little strange. It reminds me of Raul Gatto, that of course in Italy used always to call me lei, lei, lei. And then one day we were at a conference in the US, and all of a sudden he started to tell me tu, tu, tu. And then he almost apologized. He realized it was something funny. He said, but you know, we are in the States. And then he switched back to lei as we went back to Italy. Now it's okay. So I hope also with you, Yuval. Now, in this fact, by the way, Yuval, apologized that he couldn't come. He recalled to me that the first chair at Collège de France was a chair in Hebrew, because Collège de France was some kind of pendant to the Sorbonne, the Catholic Sorbonne. And also he recalled, how from the very early days he was following and also supporting, I would say, the research I was making, first with Hector, then with Hector and Miguel Virasoro and Ademollo. And I'm sure that your press reports from the US, as well as your advice, were very, very important in giving us the right direction, which eventually led from the bootstrap program that we were doing here at Weizmann to the dual resonance model and eventually to string theory. So this brings me to the subject of my talk today. You see these arrows here. Okay, up. Oh, I need the other one. So Yuval, SU3, and then from this hadronic physics came the dual resonance model, the string which was supposed to describe hadrons, and eventually the string theory we know today. So just as an introduction, let me stand here, I see better. We all know that in the second half of his scientific life, Einstein struggled quite a lot with the problem of how to combine two beautiful, successful, and certainly not disconnected theories. On one hand, Maxwell's electromagnetism that had led him to the special relativity, together with its quantum developments, photoelectric effect, down to QED, so special relativity, photoelectric effect, two of his great 1905 papers. This on one hand, and on the other hand, his classical theory of gravitation, well-known general relativity. Now, we also know that neither Einstein nor others succeeded. Perhaps Kaluza and Klein made the most serious attempts to that unification, but also that didn't quite succeed. And somehow, I think the big obstacle in making the synthesis was in the clash between the quantum, which is there in QED, and the classical of classical general relativity. And Einstein, just a year before he died, seems to have been reported as saying, I must seem like an ostrich who forever buries its head in the relativistic sand in order not to face the evil quanta. So the question I'm trying to address in this talk is what has become of this dream 50 years later. And this is the outline of the talk. I will start with a little bit of meta theory, which in part is taken after translation into English from my inaugural lecture in Paris, so that Yuval can catch up. I mean, since he couldn't attend it, you'll get a little piece of it here. And then I will go over to discussing this clash, moving on to some cosmological issues, classical cosmology, inflationary cosmology, and finally to the problems with classical and quantum Einstein's gravity. And then after mentioning a lesson we can draw from the electro-weak theory, I will move to string theory, asking Mazé, so that's the only Hebrew you will find in the talk. And finally some potential applications to black holes and cosmology. So in essence, Einstein's dream was the one of unifying at the conceptual level the physics of the quote-unquote infinitely small and that of the infinitely large, one to which quantum theory applies and one to which classical theory applies. Now, infinite is not a good word in physics, and so let's try to be a bit more quantitative about how small is small and how large is large. Now, the shortest minimal length, which is really conceivable today, at least in theoretical physics, is the so-called Planck length. It's a combination of the Newton constant, the Planck constant, and the speed of light. Its value is around 10 to the minus 33 centimeters. The associated time is 10 to the minus 43 seconds. On the other hand, the maximum length scale that we can really talk about, at least in terms of measurements, is the so-called Hubble radius, or Hubble size, which is, you know, the parameter LH, which sits in the Hubble law, giving the redshift of light as a function of distance. That characteristic distance is of the order of 10 to the 28 centimeters, or the associated time is 10 to the 18 seconds, which is basically the age of the universe, or respectively the size of the observable universe. So the ratio of these two numbers is not infinite, of course, but it's something very close to infinity, I would say, 10 to the 61. So this, in order to discuss how you can try to put together physics on so many different scales, I will use this trick, which actually goes back to Landau, I'm told, to the 30s. So maybe we will hear about it again, I'm not sure. So what you do is simply you realize that the Planck length contains these three constants in it, and you can define a space of theories whose axes are labeled by the Planck constant, the Newton constant, and the inverse speed of light. And of course, the Planck length goes to 0 whenever one of these three quantities goes to 0. And after redrawing a little bit this cube just to see it better, let's start to make, very quickly, of course, some theory of theories. That's what I was calling my meta theory. Let us indeed start with a trivial vertex where, you know, everything is 0, G is 0, H bar is 0, C is infinite. This is really the most trivial point where you have no gravity, no, you are not relativistic, and you are completely classical. If you want, is the regime where you can just use good old F equal ma and even have no gravity. If we move along one direction on one of these sides of the cube, we find Newtonian gravity. This is when we say we stay non-relativistic, we stay classical, but we add gravity to the system. So a typical system which lies on this edge of the cube is the solar system, for which Newtonian gravity works very well. Of course, there are relativistic corrections, but they are small. Similarly, if you move from 1 to 3 on that line, you are in a regime in which you are relativistic, you have to apply relativistic kinematics, but you have no quantum mechanics and no gravity. For instance, consider a particle going around in an accelerator at the speed of light. Of course, you have used special relativity, but as long as you don't make interactions, you can live just with special relativity, Lorentz contraction, time dilation, and all that. And of course, if you just move along that direction, 1 to 4, you are in non-relativistic quantum mechanics. For instance, the hydrogen atom sits down there. Now, things become more interesting, of course, when you try to move on a side of this cube. In other words, when you try to look at systems for which 2 of these 3 axes are relevant. For instance, you can try to say what happens if I have a gravitational system which also is affected by relativity. Then you have to combine these 2 theories, Newton and special relativity, and we know that the synthesis here is general relativity, is this big discovery of Einstein's in 1916. And, well, general relativity, so, I mean, in one formula, is the combination of Newtonian gravity and special relativity, and we can call it our standard model of classical gravity. Corrections to Newtonian gravity due to this relativistic effect are better and better tested as time goes on. We don't know of any contradiction so far with general relativity. General relativity also makes new predictions, like the existence of, which are not there, I mean, in Newtonian gravity, like the existence of black holes. Probably we'll hear much about that in Netzer's talk. And also gravitational wave, for which we have solid but only indirect evidence, but which are being searched for. The other most relevant phase of our cube is the one in which you combine relativity and quantum mechanics. The combination of these two, as Steve Weinberg, which we saw a moment ago, has very much emphasized in his recent books, quantum field theory is the only way to combine quantum mechanics and special relativity. So, special relativity and quantum mechanics equal quantum field theory, and particular case of this is our loved standard model of elementary particles, which again is verified even to high precision these days through many experiments. I mean, here I quote LEP because of my affiliation, but there are many other labs in the world which have contributed to establishing the standard model. Again, like for general relativity, we don't know really of any severe contradictions between the theory and the experiment. Now, I want to emphasize that the quantum relativistic nature, the fact that there is relativity of the standard model, manifests itself through particle production, through the production of real or virtual particle, and these so-called radiative corrections are really essential for agreement of the theory with the data. In other words, I want to emphasize that the standard model is not in any way a semi-classical theory, it is a full-fledged quantum theory. Well, I want to skip this, but since everybody was asking me after my talk, what about the third phase, which, which touches on this trivial point one can consider systems which are just gravitational and quantum, but not relativistic, but they don't seem to have much relevance. Actually, you can conceive such system, for instance, in string theory, but I don't know if they have really much relevance. So let me skip this to save also time. So summarizing so far, Newtonian gravity plus special relativity equals general relativity, special relativity plus quantum mechanics, standard model of elementary particles, standard model of classical gravity, standard model of elementary particles. Both work wonders, but, well, if you look at the Einstein equation, g mu nu equals 8 pi g t mu nu, this is the geometry of space-time, this is the energy momentum tensor of matter, we are a little bit puzzled because, you know, we seem to say we have to use some classical theory for the geometry, but on the other hand, matter obeys quantum laws. That sounds somewhat inconsistent. For example, we know of this dark energy, we'll hear about it. Should we think of dark energy as a classical cosmological constant, or maybe as a quantum-corrected potential energy of a scalar field? I mean, in one case we think of it classically, in the other case we think of it at the quantum level. And what about the supposed quantum origin of large-scale structure in the universe according to the present understanding through inflation? So it looks like an impossible marriage. And the issue is not just a conceptual one, this is what I want to emphasize next. It becomes physically very relevant if we move to a cosmological context. Because, appealing again to our cube, cosmology, unlike what I described so far, does really occupy all the interior of this cube. In other words, when you discuss cosmology, you cannot neglect any of those three axes. Well, perhaps you can in some particular epochs of the life of the universe, but certainly not throughout the life of the universe. The reason is that we know this, the universe expands. If we go to the far past, we find a very hot and dense universe. Very hot universe means very high energy, so we have to be relativistic. Very dense universe means very high curvature through the Einstein equation, a lot of energy. Very high curvature gives quantum processes, so we need quantum mechanics. And finally, the fact that the speed of light is finite, of course, tells us that to look far in space means looking far back in time, and this is, if you want, the deep connection between the very big length, the Hubble length, or the Hubble parameter, and the Planck time, when you look back in time. Oh. So, morale is that as we go more and more towards the past, we approach more and more this vertex number 8, which is the one which is farther from the trivial vertex 1. In other words, we would need really to understand cosmology deeply to combine Newtonian gravity, special relativity, and quantum mechanics. But you know, adding theories is not like adding numbers. You get something very non-trivial. So we already said that the sum of these two is general relativity. The sum of these other two is the standard model. But what is the sum of the sum? Okay? This is the big question. So let me go a little bit into cosmology. Well, first of all, I will go very fast on conventional cosmology. Conventional cosmology had several successes. The cosmic microwave background was the first confirmation of the Big Bang idea. Structure formation, the way structures form in the universe thanks to gravitational instability from small perturbations. Successful prediction of the light elements through abundance of light elements through Big Bang nucleosynthesis. We also understand to quite some extent how stars form and how they evolve. However, conventional cosmology has also big problems. They have problems which I would call more on the particle physics side, and then there are on which I will go very fast. We will hear more about this in the conference. And then there are problems more proper to the gravitational side, on which I will go more into. So first of all, there is this very clear matter-antimatter asymmetry, in the sense that, well, there seems to be no antimatter in the universe, 0%. However, this was a big surprise. Matter is not filling up the universe. It constitutes at most 5% of the energy density of the universe, and the rest is shared more or less in a proportion 1 to 2 between two forms of energy which are still very mysterious: dark matter and dark energy. I will not go into it because there will be more talks on this. So I want rather to concentrate on problems on the gravity side, in particular the problems of how the universe came to be so homogeneous on large scales and also spatially flat, but this maybe I will skip. However, still the universe has a lot of structure. There are stars, there are galaxies, there are clusters of galaxies. How does this structure came about? And also, I think, to be fair to this line of problems, dark energy also appears, of course, on the gravity side. As I said, we don't know exactly where it belongs. Now, this is to explain the large-scale homogeneity problem. This is a picture of how the universe expanded from the Big Bang until today. Today is this size, which, as I said already, it's 10 to the 61 Planck lengths. However, just a tiny bit, a Planck time after the Big Bang, the universe was already enormous compared to the Planck length itself, which is the size that the distance that light could have traveled since the Big Bang itself. So this is not the size of the Yuval test. It's a size of the universe at the Planck, the size of our observable universe today back at the Planck time. And this huge factor of 10 to the 30 means that there were 10 to the 90 causally disconnected regions in the universe, and we have no idea of why those 10 to the 90 disconnected regions should have had similar properties, similar temperature, for instance. And today we see that they do. So this is the homogeneity problem of standard cosmology. It's due to this particular shape of the way the universe expands. Now, inflation solves this problem by inserting a period of accelerated expansion of the universe, which is indicated here. You see this inflationary epoch, which makes it possible for the universe, for our observable universe today, to be contained early on within a Hubble radius. And that's why the universe was able to become homogeneous there. Furthermore, inflation has a built-in mechanism to create some inhomogeneities. So it is a very successful paradigm. However, it itself raises new questions. For instance, what is this, the mechanism, maybe I skipped the transparency, or yeah, I think I missed one transparency. So in order to produce this acceleration, you need a scalar field, which is called the inflaton, but we don't quite understand what this inflaton is. It doesn't look like any of the scalar fields which we know in the standard model, for instance. And where does its flat potential comes from? You need this flat potential in order to accelerate the expansion of the universe in this inflationary phase. And finally, I think most important is what determines the initial conditions that can turn on the inflationary epoch. It is not trivial. The initial conditions have to be of a particular type. So in order to answer this last crucial question, we have somehow to understand pre-inflationary physics, so to go straight into the Big Bang. But that's where we find problems, at least when we address these questions within general relativity. And there are pathologies, both at the classical and at the quantum level with general relativity. The problems at the classical level have to do with theorems due to Hawking and Penrose, which imply that under very general conditions, initial situation, initial data, as we say, perfectly smooth initial data evolve into space-time singularities, so points where things blow up. Now, these singularities, particularly these curvature singularities, quantum corrections to classical general relativity cannot be neglected. So the hope has been there for a long time that these singularities of classical general relativity can be removed by quantum mechanics. Question: can quantum mechanics remove the singularities of classical general relativity like it did with other infinities a century ago? Let's remind ourselves that Planck introduced the Planck constant to remove one infinity. Well, here, unfortunately, quantum mechanics appears to worsen the situation almost, rather than to improve it. And this has to do with pathologies which are typical of quantum general relativity. If you want, the Aviv quanta of Einstein's are back, are striking back. In fact, I mean, this can be understood if one compares a typical QED process to a typical quantum gravitodynamics, QGD, which doesn't exist, process. Okay, if you emit a photon, if an electron emits a photon and reabsorbs it, yes, it leads to some infinities, but you can handle them, and in the end, you get some calculable corrections, like corrections to G minus 2, or the Lamb shift, which are calculable and can be checked against the data. This cannot be done for gravity. The infinities are much worse, and the corrections due to these diagrams are really uncalculable. And furthermore, these infinities propagate down to low energy. It's not just that they affect gravity near the singularities. If you are really if you're really doing your calculation, even at low energy, the problem is this fact that the virtual quanta can be very energetic. So even if the external energies are low, and you consider a low energy process, the fact that you can create very energetic virtual quanta kills you. Okay. So, to be sure, there are, I repeat, pathologies even in quantum field theories, even in the standard models, but the difference between the situation in the standard model and in general relativity is that in the first case we can tame the infinities. In fact, today, because of these infinities, even quantum field theories and the standard models are viewed as effective theories, which are approximately valid below a certain energy scale or above a certain distance scale. And the difference between what we call renormalizable and non-renormalizable theories is really in the price to be paid for our ignorance about what happens above that energy scale. If you want, in a renormalizable theory, the price is finite. For non-renormalizable theories, the price is infinite. There is an instructive example of this, which is Fermi versus the electroweak theory. In Fermi's 1934 theories, the neutron beta decay was described by a point-like interaction between the neutron, the proton, the electron, and the neutrino. In today's view of the process, it looks much more complicated, but it's actually simpler from our point of view. Of course, the neutron is made by quarks, as Yuval has found out, the proton too, and then there is this exchange of a W meson between quarks and the electron and the neutrino. And the interaction, therefore, which is occurring at a single point in space-time here, is mirrored over a finite region of space-time because of several things, but in particular because the W meson travels a little bit, okay, before producing the lepton pair. So, to be sure, even the electroweak theory, the one we use today, of Glashow-Weinberg-Salam has infinities, hence uncalculable parameters like, I don't know, alpha or the Weinberg angle, yet it is much more predictive than Fermi's theory, okay? Where you cannot compute radiative corrections. So the question is it possible to do something similar in general relativity? A priori, this looks like an impossible dream, once more, because general relativity is based in an essential way on the existence of a space-time continuum, coordinates, which are used to establish coincidences of events in space and time. But yet, string theory, and now we'll finally come to it, seems to be capable of realizing that dream, and indeed it does through something that we may call quantum miracles. So quantum mechanics will enter in a very crucial way in achieving the goal. So here I come to my mazé. What is it for the few who don't, whose Hebrew is worse than mine? Somebody has put it in the, I don't know the author of this sentence, maybe you can help me. String theory is the theory of strings. It looks like tautological, but it isn't. It says that string theory has very modest origin. You don't start from ground principle like the equivalence or the gauge principle, but just an assumption that everything just quote unquote is the big assumption, but still, that everything is made of relativistic quantum strings. Okay, these three keywords. So strings plus special relativity plus quantum mechanics, that's it. Grand synthesis. How? Well, it's because of quantum miracles. You see, while if you take a classical relativistic string, a little string which vibrates, which has a tension T, it can have any size, let's call it L, and therefore any mass, because the mass is proportional to L through the tension. But on the other hand, if you take quantum strings, they have a minimal, or rather optimal size, which is called the string length Ls. It's very similar to the Bohr radius. I mean, the Bohr radius is an optimal radius to minimize the energy of the hydrogen atom. If you make the radius bigger, you get bigger energy, but also if you try to make it smaller, you get a bigger energy. And it's very similar. It's actually more similar to an harmonic oscillator. But, okay. And the string length, you see, is given by, it's a square root of h bar over t. Notice h bar. Okay. So this length, why does it appear? Well, it appears very naturally in the action of a string. A string has a classical action which is proportional to the area swept by the string as it moves in space-time, and the proportionality constant is the tension. When you go over to the quantum theory, you need this dimensionless quantity, which is s over h bar, and therefore you get the area divided by an area. What else? That area is the square of this length. It's as simple as that. Now, this fundamental size of the string, this is what smears the interaction, because you see, while in quantum field theory you have these point-like vertices, in quantum string theory you have these non-point-like interactions. You don't know exactly where the interaction takes place. It's, you know, two strings which combine to give a third string. And how do you describe, for instance, a scattering process in which two particles come in, maybe form another particle and then decay into two different ones? Well, here it is. You see, the strings combine and then there is a second major miracle. Okay, so this is what smears the interaction. The other very important miracle is that if you take classical strings, they cannot have angular momentum without having a finite size. Well, it's just any system, if it doesn't have any size, it doesn't have angular momentum, right? Because there is no R. But if it has a finite size, it has finite mass because of the tension. So this is the classical picture. Now, what happens at quantum, in the quantum theory, it's again a miracle. Quantum strings may have up to 2 units of angular momentum, units of h bar, of course, without acquiring a mass. In other words, while classical you have the following inequality, m squared over t bigger than j, In the quantum theory, you have plus h bar times a sum, which is formally infinite. You have to see how you have to regularize this infinity, but there is a unique way to do so. And in the end, you end up with a negative. As often happens, the sum of an infinite number of positive things gives a negative result. So you get minus, this is a very crucial, it's like a Casimir energy in a sense, alpha 0 h bar. So, where this alpha 0 is quantized, it can be, depending on the type of strings, open, closed, fermionic, bosonic, it can be 1/2, 1, 3/2, 2. So you see, this allows for massless m equals 0 strings which have non-trivial angular momentum. That non-trivial angular momentum can be 1/2, 1, 3/2, 2, and also 0. So in picture, this means the following, that if you plot m squared and j on this plane, there is a classical boundary, which is this diagonal, below which states are classically allowed, above which states are classically forbidden. But thanks to this quantum miracle, the boundary is not so strict, and you get these extra states which are quantum allowed. And if we blow up, in particular, the massless sector, we find that the massless sector has spin 1/2, spin 1, spin 3/2, and spin 2 particle, massless particle. In particular, an open string can give a photon, a j equal 1 massless photon, and other gauge bosons. Other can originate actually from a stringy version of the Kaluza-Klein mechanism. And a closed string can give objects like a spin 2 massless graviton or a spin 0 massless dilaton. Now, the integer spin massless states are typically what we need as carriers of interactions. Gauge bosons and gravitons respectively give gauge and gravitational interactions. The half-integer massless states, these are massless at 3 level. Hopefully they will remain light as we add radiative corrections, which are finite, and those should provide the constituents of matter. So if we combine these first two miracles, we get to a unified and finite theory of elementary particles and of their gauge and gravitational interactions, which are not just compatible with quantum mechanics. The whole thing is based on quantum mechanics. It's stronger than that. So you can say that relativistic sand and evil quanta happily coexist in string theory. There are also some, what I would call minor miracles, but I think they're still worth mentioning. They are not essential, but they are interesting properties that the theory has. For instance, classical strings can move consistently in any ambient space-time, but this is not the case for quantum strings. They require particular, what we call target space-times. Otherwise, there are terrible anomalies that kill the theory. For instance, a Minkowskian space-time, flat space-time, must have 9 space and 1 time dimensions. So, since we only observe 3 space dimensions, 6 of them must be compact and small. But how small, you can say? This was one of the problems with the old Kaluza-Klein theory. You did not know why these compact dimensions didn't shrink to 0 size. Well, there is a symmetry called target space duality, which guarantees to be distinguished from Horn-Schmidt, Dolan-Horn-Schmidt duality, by the way, which guarantees that the compactification radius RC is equivalent to a different compactification radius L string square over RC. So you see there is a transformation between, say, a very large compactification radius and a very small one in string length units. Now, there is a fixed point of this transformation when this is equal to this, which is, of course, RC equal LS. And this is a natural stabilization point for the compactification radii. And when you sit down at this value of the compactification radius, there are new non-abelian gauge interactions that emerge through, as I mentioned before, a stringy version of Kaluza-Klein. And finally, this plus other so-called strong weak electric magnetic dualities unify conceptually all known consistent quantum string theory in what is called M theory. Let me not go too much into that. Oh, there is a fourth one, which is also very interesting, and that the theory has no free parameters. Parameters that usually have in quantum field theory, like the fine structure constant, are replaced by scalar fields whose vacuum expression values should provide, hopefully in some dynamical way, through some calculation even, the constants of nature, for instance, the fine structure constant. Now, there are also problems, potential problems. Is my watch going?
10 more minutes.
Oh, I see. I think it stopped. My watch.
You had to watch that.
No, okay, no, that's it. I have 50 minutes.
15.
Okay. So, this scalar field have vanishing perturbative mass because of supersymmetry. Now, the question is whether they remain light even as you add all the corrections due to loops, radiative corrections, and so on. If they do, then they may induce short distance, how short we have depends on how light they remain, modifications of gravity. They can threaten the equivalence principle and the universality of free fall if this is very long range forces, and even induce space-time variations of the above constants. Because, you see, if the fine structure constant becomes a field, you can ask, why this field has a fixed expectation value? Why doesn't it change from time to time or from place to place? This is a very active field of experimental and theoretical research, and I think that Harold Fritsch will mention this. Then I will move, to conclude, to some physical applications of string theory. One is in the context of black holes, strings, and quantum mechanics, which is a very interesting, conceptually very interesting arena. And the second is primordial cosmology. As far as string and black holes is concerned, again, this fundamental length of string theory intervenes in establishing a boundary between what can appear as black holes and what cannot appear as black holes. In other words, if I consider the mass of the black hole, say on this axis, and the string coupling constant, because there is a string coupling constant which is a scalar field, and for the moment let's consider it to be arbitrary, there is a curve in this plane above which black holes should be there, but below which black holes can no longer exist. Well, the reason is that if one state over here would be a black hole, you would discover that the Schwarzschild radius of the black hole would have to be smaller than the string length itself, which, as I said, plays the role of a minimal length. Or the Bekenstein-Hawking temperature of this black hole would be higher than the so-called Hagedorn temperature of string theory, which is supposed to be an upper limit to temperature in string theory. That has interesting conceptual consequences because an interesting problem, theoretical problem in a Gedanken experiment is what happens to an evaporating black hole. You know that black hole evaporates through the so-called Hawking process. So as they evaporate, they lose mass, they increase their temperature. And you see, if it was not for this curve, they would run down to zero mass and infinite temperature, hitting some kind of singularity. And it seems that, the existence of this curve allows to avoid the singularity. Once more, because of the presence of this fundamental minimal length in the theory. I see here something got wrong. So we can even study in string theory the entropy of black holes and the information paradox problem. You see, in some favorable cases called BPS, string theory allows us to give, for the first time, a statistical interpretation to the thermodynamic Bekenstein-Hawking entropy of a black hole. This is this famous formula of Bekenstein and Hawking, that the entropy is proportional to the area in Planck units. This is what I call capital L Planck before, sorry for that. Now, however, you see, for a long time it was not possible to give a statistical interpretation of the entropy as the logarithm of the number of states. And in some favorable cases, string theory has achieved that. And string theory also offers convincing arguments, in particular through the holographic correspondence between gravity and gauge theories, against any loss of quantum coherence in processes where a black hole is formed from a pure state and then undergoes Hawking evaporation. And in fact, recently, Hawking himself took back his previous claims to the contrary, and I think largely because of stringy evidence for the preservation of quantum coherence. I also wrote a paper recently on an explicit unitary S matrix that can show how this coherence is preserved. I couldn't, unfortunately, go really straight into black hole, the black hole formation region, but near the threshold of production of black holes, it all works fine. And finally, cosmological applications. Well, we know that string theory resolves, indeed, certain singularities of general relativity. Remember, I started by saying, does quantum mechanics resolve the singularities? We had problems with the usual way of approaching quantization, and then we went to string theory. Now we have to come back to the problem of singularities. Are they really resolved in string theory? Well, those associated with certain kind of singularities are certainly resolved. Those associated with cosmology, like the Big Bang singularity, are harder to deal with because of technical reasons. It is likely that there too the singularity is either eliminated or reinterpreted in terms of new degrees of freedom which become relevant as you approach the singularities, which are not the usual way you describe the metric, for instance, space-time. If so, we may conceive new cosmological scenarios in which the Big Bang, rather than representing the beginning, is the result of a previous phase in which space-time curvature, in particular the Hubble expansion parameter, grows instead of decreasing. It grows towards a maximum, and there would be a string phase which would make the universe bounce from this phase of increasing curvature into a phase of decreasing curvature, which is the one we live in since the Big Bang. So the Big Bang becomes, if you want, a big bounce. And these scenarios can solve in new ways the problems of standard cosmology, because if you remember, our problems was that the universe was too big for its young age. Was this 10 to the 30 times bigger than it should have been. Now, if you make the universe older instead of smaller, you pretty much achieve the same goal. So this is a picture of how, in this other scenario, you may solve the horizon problem. Now, the interesting thing is that these cosmologies, called sometimes pre-Big Bang cosmologies, have even observable consequences and, in principle, can be tested. And the reason is not new, is the one which is also invoked for observing the inflationary epoch today. The reason is that perturbations on scales larger than the Hubble radius, for instance, a perturbation on a scale which is larger than this distance, this red distance, freezes out and therefore is transmitted from the early universe until now practically unchanged. I mean, to be more precise, it is just redshifted. So by observing inhomogeneities today on certain scales, we can reconstruct what happened in the early universe. And that's why if you change the early universe according to string theory, you should find something typical of that in today's observations. And just to make a few examples, for instance, in this model, you predict a stochastic background of gravitational waves, which should be everywhere in the universe, and depending on some parameters, which unfortunately are still phenomenological, we cannot compute them, this is the curve or whatever gravitational wave background, And these are the advanced LIGO, Virgo, and LISA sensitivities. So you may be able to see this stochastic background. There are also mechanisms to produce seeds for magnetic fields, which then could be responsible for the presently observed intergalactic or galactic magnetic fields. And there is also some new mechanism for generating CMB anisotropies without any tensor contributions, which again could have some, could be tested by new experiments like the Planck experiment. So I conclude, last two transparencies. So to conclude, it seems to me that Einstein's dream really appears to be realized in string theory, but in a way that could have been hardly imagined 50 years ago. String theory was born not by accident, but actually because QCD and apparently nature has string-like object excitations, and this is because of quark confinement. Now, the true QCD string is still to be discovered. So the one we were after, if you want, in those days is still something we don't know. I mean, there is a lot of activity on this still, but it's still not there, the solution. While the strings we have known since the late 60s found in applications, again, that no one could have imagined at the time. Again, I don't know, I think it was Sergio Fubini who said this was like a piece of 21st century physics that fell too early on us, this string theory. So the dream gets realized thanks to and not against quantum mechanics. And I want to emphasize, its starting point is not a classical field theory. It's not that you start with Maxwell and general relativity and you try to quantize those theories with much pain, if at all, you know, you can make it. In fact, without quantum mechanics, strings do not yield either a photon or a graviton, and thus neither an electromagnetic or a gravitational fields. These classical descriptions of physics only emerge as some large distance or large occupation number limit of something which is fundamentally quantum, a quantum string. So Einstein's dream comes true, as I said, at the theoretical level at least, because as Shimon's poem emphasized, we don't know whether it's true, but conceptually it seems to work, but it's quite the opposite of what Einstein himself had been pursuing. So maybe he would have reacted to string theory like he did to quantum mechanics by saying that God doesn't play strings. We will never know what Einstein would have said, but we can try to find out instead what nature actually does. And meanwhile, many, many happy birthdays, dear Yuval. Thank you.
We thank Gabriele for his beautiful talk and about telling us about the marvels of strings. And we have time for some questions. Marek.
This is related to the part of your talk where you talked about the pre-Big Bang.
Mm-hmm.
Recently, there has been a very controversial paper by Kolb and collaborators.
Yes, I know.
Trying to propose that dark energy can be explained away, essentially, by Planck fluctuations. Do you have any comments?
Okay. Well, it doesn't have much to do with my talk, but I happen to have seen the paper and to have even tried to study it together with a student. It's actually, I don't think it's actually, well, you know, Kolb writes many papers, so I don't know if we are talking about the same. But there's been recent papers in which they try to say that the acceleration, the present acceleration of the universe is due to fluctuations, to inhomogeneities. Now, there were two papers. In the first one, these were fluctuations on scales which are larger than the present horizon. I think now, at least one of the collaborators officially told me that he's taking that back. Okay? It looked very suspicious, and now they don't push it anymore. They still say that inhomogeneities inside our present horizon may be able to do it, that you cannot use the usual, Friedman equations, because averaging the equations, the two equations, is not the same as writing the equations for the average. There are some extra terms. This is well known from any time. I remain very suspicious that with things, you see, when it was outside the horizon, you could say, well, what is the equation of state of a perturbation outside the horizon? I'm still very suspicious that somehow the perturbations inside the horizon can give an effective negative pressure that can produce acceleration. So I'm skeptical, but I was discussing with these people just a week ago, so very interesting. Yuval.
Okay, any other
Yuval.
Yuval, of course. Wait, Yuval.
A comment on, I published 2 or 3 years ago a conjecture that perhaps one can draw from the black holes a lesson on life and evolution. The connection being the following. There is this result that you recover Bekenstein
Hawking.
contribution
Yes.
in these examples that
Yeah.
studied subject. Now, and I remember that when Amnon Aaroni did his thesis at ago, he did not have Bekenstein entropy. And we had a problem that what happens when everything concentrates to one point in a, and then it means that there's more order, so it looks like a negative entropy. Bekenstein term correctly. Now, in evolution, there is something similar. There is the Kolmogorov entropy. And it in complexity, it increases. So the sign goes in, Schrödinger said that in What is Life, he said that evolution creates negative entropy, because it creates order. But on the other hand, if you take Kolmogorov's result, then you have additional entropy. So my conjecture was that maybe other interactions also have a contribution of some kind. Thermodynamics was defined for 3 particles. So all the complications came from there is also interactions. So it could be that the combination of the various forces that create a living being and so forth adds a certain entropy that can be recovered if you take step by step.
Well, okay. Of course, your question is very deep and difficult. So I will not try to answer that directly. However, let me say that this problem of entropy, in particular, you want to produce a Big Bang. Say, let's talk now not about black holes, but rather about this cosmological scenario that I was proposing. One of the big problems is to produce a Big Bang which has the right amount of entropy. Now, the entropy at the Big Bang is pretty low. It's not zero, of course. But it's pretty low, and this is believed to be the origin of the error of time. I mean, this is why, we have a well-defined direction now of entropy increase. Had the entropy been maximal already at the Big Bang, there would be no way to create order and so on. So now it seems that I didn't have time to explain, but I mean this pre-Big Bang phase seems to be capable of doing something perhaps like what you want, in the sense that a certain region of space which undergoes some kind of collapse will get a relatively low entropy without contradicting the second law, because some entropy will be sent out to other regions. So the question is whether you can create a large enough bubble of low entropy in which we are, okay, which is big enough to contain our present universe today. And this, I think, is a very interesting issue. So, and of course, I mean, this is related to the origin of life, of order, and so on. But, I mean, the reason, I mean, Penrose wrote also about that, that, of course, the reason why why there can be life and order and so on here on Earth is because there are low entropy sources of energy, which is the sun in our case. And the Earth sends back this energy in low frequency modes with a big increase of entropy. So the question is how come, however, the entropy was small to begin with? If you try to follow this argument, you go back and back and back, and you find finally that the big puzzle is why the entropy at the beginning was small.
Okay. Aaron?
Let me ask the simple-minded and obvious question. I mean, when Yuval did his SU3, he predicted the omega minus, and it was found experimental, and wow, everybody believed. I'm sure you believed the string model.
I used to believe the old one, and then I disbelieved it.
What should happen that I should also believe it?
It's a $1 million question. Look, I think there are different possibilities. Of course, one would be if string theory would be pushed so much. You see, you have to realize that it's a relatively new theory, and that it took 40 years between the beginning of quantum field theory and the standard model. So, and we still don't know very much string theory at the so-called non-perturbative level. It's like if you have QCD and you have quarks and gluons, you don't have the slightest idea that they are confined, and you say, well, so how do I check the theory? So it may take a long time. Now, it could be that one possibility would be that string theory really predicts 3 families of quarks and a good gauge group. For the moment, it doesn't. It allows certain possibilities, but it also allows millions of others, and so one possibility would be, you get convinced because, there is no reason in quantum field theory why you should choose a certain gauge group, certain representations, and so on, and string theory could give that answer. The other possibility is that you find tiny new effects which are very hard to imagine in a conventional context, like what I mentioned, slight variation of constants, some new forces due, for instance, to this dilaton, which we know how it couples and so on. So if we knew its mass, we could predict that there is a force with some characteristics and so on. So precision experiments. And the third, in my opinion, and perhaps the one I believe more into, it's through cosmology. Because through cosmology the universe is the biggest accelerator we have, okay? Sorry for the last talk. But this, we know with accelerators we will be able to go back to some time in the early universe, but not extremely, extremely far away. Already, you see, when you test inflation today, you are testing physics at very, very short scales. So the hope is that in cosmological data there will be a trace of what happened in the early universe, and that could be affected by string theory. But again, even there, technically, we are still far from being able to make solid predictions.
Okay, so the last one, please.
Just like that.
Microphone.
At the present state of the universe, we have 2 models of matter: the background matter and very high energy particles, cosmic rays. And these 2 models are in about thermodynamical equilibrium, because from the background plasma you accelerated high energy particles, you have cosmic rays. What is the situation when the universe with the evolution of the universe? It's the first question. And is there some place for cosmic rays as very high energy particles in the string field?
Well, I doubt I can give much light on these issues. I mean, I don't think, to be honest, I don't think that string theory, for instance, has given new ideas of the origin of ultra-high energy cosmic rays, as far as I know. And you were asking about the evolution. In the future evolution of the universe, what would happen to the, to what? Yeah. No, okay, look, I better say we have to discuss it in private, because I don't dare to make any strong statement here.
Okay.
It's an interesting question, though.
Okay, so we will thank Gabriele again for his talk. And